Hello everyone, this is the brief overview for week 3 session of HSCI 6263. The discussion points for this week would be inferential statistics, and along with them, the one-sided and two-sided hypothesis testing, p-values, confidence interval, one-sample testing, and distribution-free or non-parametric tests. You are expected to read chapter 5 of your textbook, but actually chapter 4 also has a good discussion about estimation and hypothesis testing, so I also recommend you to revise those sections in chapter 4. Up until now, the discussion was more focused on descriptive statistics, which are values that describe the characteristics of a sample or a population. And moving forward, we will discuss more about inferential statistics. Inferential statistics is a branch of statistics dealing with drawing conclusions, generalizations, predictions, and estimations based on data from samples. So basically, we have a bigger population, we draw a sample from it, and then we will draw conclusions about the population based on the sample that's used. And drawing conclusions from a sample data could be based on estimation, or it could be based on hypothesis testing. Hypothesis testing is an essential procedure in statistics. A hypothesis test evaluates two mutually exclusive statements about a population to determine which statement is best supported by the sample data. Please watch the supplemental videos that are on the weekly session. They provide details about the steps to hypothesis testing and also non-directional and directional hypotheses. In the last week's session, we looked at the binomial distribution, the Poisson distribution, and normal distribution. And there's a couple more distributions that we have to be familiar with, one of which is the t-distribution. The t-distribution is a continuous probability distribution that's used to estimate population parameters when the sample size is small or when the population variance is unknown. According to the central limit theorem, the sampling distribution of a statistic, like the sample mean, would follow a normal distribution as long as the sample size is sufficiently large. Therefore, when we know the standard deviation of a population, we can compute the z-statistics and use the normal distribution to evaluate probabilities about the sample mean. But sample sizes are sometimes small, and often we do not know the standard deviation of the population. When either of these problems occur, statisticians use the t-distribution. The t-distribution is also referred as the student's t-distribution, and it has the following properties. The student's t-distribution is different for different sample sizes. It has the same general symmetric bell shape as the normal distribution, but it reflects greater variability that's expected with small samples. The student t-distribution has a mean of t equal to 0, just as the standard normal distribution has a mean of z equal to 0. The standard deviation of the student t-distribution varies with sample sizes and is greater than 1. This is unlike the standard normal distribution, which has a variance or standard deviation of 1. As the sample size n gets larger, the student's t-distribution gets closer to normal distribution. if we look at the z-distribution and the t-distribution side by side, both of them have the sample mean centered at the population mean. However, the z-distribution has standard deviation while the t-distribution has standard error. The sample mean for a z-distribution has a normal distribution, while the sample mean for a t-distribution follows the t-distribution with n-1 degrees of freedom. Degrees of freedom generally refer to the number of independent observations in a sample minus the number of population parameters that must be estimated from the sample data. Degrees of freedom are number of independent pieces of data being used to make certain calculation. The more degrees of freedom we have, it's usually the more certain we can be that we have accurately sampled the entire population. Another commonly used statistical distribution is the chi-square distribution. Chi-square distribution with k degrees of freedom is a distribution of sum of squares of k independent standard normal variables. Thus, if we have z1, z2, z3, up to zk standard normal random variables, each of them with the mean of 0 and standard deviation of 1, and if they are independent, then z1 squared plus z2 squared plus z3 squared up to zk squared would have a chi-square distribution with k degrees of freedom. The degrees of freedom refers to the number of independent standard normal variables involved. That's because these k variables are independent and we can choose them freely and independently. The chi-square distribution has the following properties. The mean of the distribution is equal to the degrees of freedom. The variance is equal to 2 times the number of degrees of freedom. And as the degrees of freedom increases, it approaches the normal distribution curve. Since p-value is a probability, it's a number between 0 and 1, and it's interpreted as follows. A small p-value, typically, we compare p-values with a threshold of 0.05, and a small p-value indicates strong evidence against the null hypothesis, so you reject the null hypothesis. On the other hand, a large p-value, which is a p-value that's greater than 0.05, indicates weak evidence against the null hypothesis, so you fail to reject the null hypothesis. P-values that are close to the cutoff or the threshold, which is 0.05, are considered to be marginal. Confidence intervals are another important tool for inferential statistics. A confidence interval gives an estimated range of values or plausible values, which is likely to include an unknown population parameter. This range is calculated from a given set of sample data. To construct a confidence interval, we would need the point estimate of the population, the level of confidence, and the standard deviation. The level of confidence in a confidence interval is a probability that represents the percentage of intervals that would contain if the large number of repeated samples are obtained. Hence, confidence intervals are calculated with the point estimate, which could be a sample mean, or it could be a proportion, or etc. It would be bounded by lower and upper boundaries, which would be plus or minus a confidence level times a standard error. The confidence level varies depending on the sampling distribution of the statistic. So for means that are normally distributed, we could use the z-distribution. And for unknown variances, we could use the t-distribution. And for proportions, we could also use the z-distribution to calculate the confidence intervals. Suppose we obtain a simple random sample from a population. Provided that the population is normally distributed or the sample size is large, the distribution of the sample mean would be normal with a certain mean and standard deviation. Since the sample mean is normally distributed, from last week's lecture, we know that 95% of the sample means should lie within 1.96 standard deviations of the population mean, and 2.5% will lie in each tail. A 95% confidence interval means if we obtain many samples of sample size n from a population whose mean is unknown, then approximately 95% of the intervals would contain mu. The same interpretation could be used for a 90% confidence interval or for 85% of confidence interval, and etc. One sample test is the other topic for this week. It's applicable when we are trying to make inferences about a sample that's taken from a single population. In clinical trial setting, it could be a sample that is from pre and post treatment of subjects that are in our study. It could be measurement of their systolic blood pressure before treatment and after treatment, or it could be about their weight, or it could be about any measurement, but it's something that's repeatedly measured from the same population. One sample test is also applicable when we try to compare data to a pre-specified value. We have one sample that's collected and we try to assess if our sample mean is different from 0 or if it's different from a certain pre-specified number. And it could also be used for proportions as well. One of the most commonly used one-sample tests is a pair t-test. Let's look at pair t-test with an example. Let's say we have a study that has 15 subjects. And in this study, we are trying to assess if a treatment helps the subjects in losing weight. For all the 15 subjects, we have measured their weight prior to the treatment and also after the treatment. And the measurements are in pounds and presented in this table. If we look at the descriptive summary of the sample, the average weight for the subjects before the treatment or pre-treatment was 305 pounds with a standard deviation of 70. As you see in the table, other descriptive statistics are also presented. Similarly, for the post-treatment, descriptive statistics are presented, and as you see, the mean was 259 pounds with a standard deviation of 59. Just by looking at these statistics, I can tell that the treatment helped the subjects in losing weight. So, to support my finding, I went ahead and calculated the p-value using per-t-test, this calculation is using a statistical software that's called SAS. The average difference for pre and post that's observed from the 15 subjects is 45 pounds. And the 95% confidence interval around this difference was 40 to 52, which means that the population mean could be as low as 40 or as high as 52. And this difference apparently was much less than the normally used threshold of 0.05, and hence we can conclude that there is a statistically significant difference between pre and post measurements. So basically we're saying that the treatment helped the subjects in losing weight, and this difference was statistically significant. When we have a single sample population for categorical variables, we can use the chi-square goodness of fit test to determine whether a sample data are consistent with the hypothesized distribution or not.